Toplanan ve geri dönüştürülen plastik gıda ambalajı tasarruflu bir ampule dönüşerek yeni bir enerji kaynağı olabiliyor. PAGEV, plastik sektörünün birleştirici gücü. Toplanan ve geri dönüştürülen boş gıda ambalajı pratik bir ürüne dönüştürülebiliyor. Böylece plastik atık günlük hayatta ihtiyaç duyduğumuz yeni bir ürün olabiliyor. PAGEV, plastik sektörünün birleştirici gücü.
İsmim Eralp Demir, ben Sabancı Üniversitesi'nden geliyorum. Fakülte üyesiyim orada. Aynı zamanda Kompozit Mükemmelliyet Merkezi'nde görevliyim. Tasarım analiz grubunda. Yani bu eğitim olduğu için biraz böyle teknik ağırlıkta yaptım. Yani biraz ağır olabilir ama mümkün olunca hafifletmeye de çalıştım content'i. O yüzden kusura bakmayın. Yani öğleden sonranızı biraz ruhun ettiysem. Çok fazla terminoloji var. Hepsi İngilizce gibi. İster İngilizce yapabiliriz, ister Türkçe yapabiliriz. Benim için çok şeydi ama İngilizce yapmayı tercih ederim. Çünkü bu sefer şey gibi oluyor. Biraz karışık oluyor. İlk önce size biraz merkezimizden bahsetmek istiyorum. Kompozit merkezimizden. Yeri üniversite kampüsünde değil, Teknopark'ın içerisinde. Fakat Sabancı Üniversitesi'nin bünyesine dahil. Burada çeşitli konularda, okay, let's do it in English. We are doing some research in different fields. One of them is micro nanoscale technologies like graphene or other polymer-based technologies, who Yusuf Hoca and others working on. There is an additive manufacturing division. There is metal additive manufacturing device group. And some metal additive devices like DMG Mori and EOS 290 or some stuff like that. And we have also some polymer printing equipment. Bahattin Hoca is leading that group. There is also unconventional manufacturing and konvansiyonel olmayan üretim and machining group, where we have water jet cutting, for instance, or like AFP that Cengiz Hoca talked about in the morning. It's automated fiber placement method, this kind of equipment. And we have also a composite division. Actually, Taner Hoca is leading this group. And there is also advanced composite manufacturing lab, where we have a clean room, we have all kinds of like presses, I know, like equipment that are necessary to do the composite manufacturing. I'm not a composites guy actually, so I'm more like in the numerical simulation kind of group. So me and Murat Hoca are working together in the theory and simulation group. Okay, so today I divided the content into 3 parts. First is like, I literally took it as a training, so I wanted to give first an introduction to finite elements. What is it? Okay. And then I will talk about how is it different for composites? Okay. What is different for composite? What difference we need to do to analyze composites? And the third, I thought it could be an interesting topic. What should we do, or what are the design methods for variable stiffness composites? I will explain what all mean. So I thought from basics to advanced. This is a whole course, like a 1 semester course. So don't expect me to give you the whole thing in 1 hour or half an hour. So I just tried to make it short as possible. Okay. And also this is some part of some chapter in my solid mechanics class. So and this is a research topic actually I'm working on currently. So please feel free to have any questions. Stop me, say, just do it in a casual way, okay? Just ask any questions in your mind. Okay, so introduction to FEM. First, why do we do FEM? I need to do some basic definitions. I know there are lots of people from different variety of background. And what is discretization? I will do a 1D FEM example to show you the concepts of finite element method, and then a commercial FEM application. So in design in many of the different various fields, starting from biomechanics to, I know, metal forming. Everywhere you have seen finite element applications, because nobody solves problems analytically anymore. So it's a computational tool. And with the advances in the computation power, you are able to do a lot of precise calculations. So these are some examples, and there are lots of commercial software available: ANSYS, Mark, Abacus, COMSOL, Elestina, Siemens NX, and many others. Maybe I don't know their name. So it's a very commonly used method to analyze structures, mechanical point of view, dynamical analysis, all kinds of analysis, and fluid-solid interactions, and like in here, and so on. Okay, so basic idea is you basically have a structure, and you have some loads on that structure. You specify some displacements. The loads and displacements are both called boundary conditions. And then you analyze your structure, look at your stresses, and you design iteratively on that. So some basic definitions. What is a strain? When we talk about strain, there are two kinds of strain. One is the normal strain, where your strain is along your unit. Let's say you're displacing. Let's say you have a cube. Let's think about this simpler way. You displace it with certain amount. It is the ratio of this displacement to its initial length. Okay. So it is like that, and we have it in 3 dimensions. So it has, these are 3 normal strains components. Okay. And we have also shear strains. Apart from that, different from the normal strain, this time your displacements are transverse to your initial length. Okay, this is the difference. And you basically, you have, I call this baklava, so it resembles me that. And then you have, this is pure strain condition. It's called pure strain. Okay? And so I will just skip some of these, not to get you bored with this. So in the end, you have a symmetric strain, shear strain. So, and similarly, you can do you have the shear strains in the other 2 directions. Okay. There's only one thing that is sometimes confused with people. Normally, the material has shear modulus, G. You must have seen somewhere. That is measured for this condition because it's experimentally easier to do this, right? Have this condition than this. You hold the material here, you push it there, and you can find shear modulus experimentally much easily. So that's why those shear moduli are defined over this simple shear. Simple shear. But this is pure shear. So when you think of this simple shear, it is just this shear plus you rotate this, 1/2 of the angle, you got this. This is just one definition, usually confused with among engineers, so I will come to that why it is very important. Okay, continuing with the definitions. Now, if we put these strain components, we have normal strains, 3 normal strains, 3 shear strains. We put them all together, we got in the end, a strain tensor. It's not a vector, it's not a scalar, it's a tensor. It's a 2nd rank tensor. So you put these diagonal terms as your normal strains, and these are your shear strains. You got this strain tensor. Okay, so these are infinitesimal displacements. So in the end, in the limit, these become partial derivatives. Okay, so you represent this way. Okay, and like we said, it's a 2nd rank symmetric tensor. I have cut some of the definitions, so you can find it in the notes. I think if they will bring it over to you. What else? We have stress. Stress. When we say stress, usually people think that it's a scalar quantity. It's one of the common stress measure that is used is Von-Mises stress, which is a scalar quantity of your material stress. But but computed from all of the stress components. So you can have, you should maybe seen somewhere the components of stress. It is called vectorized form, or it's called a direct notation. But let's not go into that too much. But in the end, if you put these on the right form, stress is actually a second rank tensor. We have this unit cube here. You know, I was an engineer back in the times. We always have strength of material courses and stuff. I'm graduated from mechanical engineering, and there, when I graduated, I didn't know that stress is actually a tensor. I thought it's always like it's a vector, but it's mathematically a tensorial quantity. The reason for that is, just to give you an idea, stress is defined over force, over the area. Both are vectors. Force is a vector, area is a vector, so stress is a second rank tensor. Okay. So this part of the presentation, I will get you bored a little bit. Sorry about that if I'm doing that. Okay, so how do we couple stress and strain? We define stress, we define strain, and how do we couple it? We do it coupled by constitutive model. What kind of constitutive models we can have? The easiest one is elastic one. Stress is linearly proportional to strain, which we define modulus. It's a matrix, okay? But it's not just a constant, it's not just a module, but it is a matrix, okay? Sorry. Now, I start with compliance always. It's easier, you don't have to memorize anything with that. It's much simpler to realize. And this is like you have 3 stress components, compliance relates to the strain components. You can reduce it to 2 dimensions. You have stress components, and you can find the strain components out of it. This is called the reduced form of this compliance. Okay. All right. Before moving on, I just want to show you one thing. What this means. Does anybody know what E is? Anyone? Young's modulus? Yeah. What is nu? Poisson ratio. For an isotropic material, we have 2 independent parameters. And that's it. 2. And then you define shear modulus is actually a function of these 2. Okay? So now think about it. Let's say I just apply tension. Sigma xx, let's say. Okay? I have just a number for this. These are 0. Okay? What it does is I got some strain. Like I multiply this vector with this matrix. I got these 2 terms coming up, right? These 3 terms. This. You multiply with this, and so these will appear. This will be sigma xx over E, right? This will be sigma xx times minus nu over E, right? So I have tension. It expands along the tension direction, but it also contracted. It's called the Poisson effect. It contracts also in the other lateral direction. These 2. So it's easier to visualize. So usually when you invert this, you got some coefficients, a function of these numbers. But I don't like memorization, so I just want to keep this form. Okay, we have talked about that this is we investigate force balance. I'm not going to go through the mathematics behind it. You can look at the notes there. I added them. We are basically solving for Newton's second law, F equals ma. The rate of change of momentum is equal to the force. And coming to finite elements, what do? We have a body, a continuum body. In finite elements, we discretize it into elements and nodes. So we have like if you think of this like a cake, I divide this cake into pieces, and I call them each of them an element. And the element has, you see, has some connection points. They are connected to each other at certain points, and to the body. They are called the nodes. Okay? So 2 things define this. It's called a mesh, or finite element mesh. Sonlu eleman ağı. the nodal coordinates, the coordinates of these nodes, and the element connectivity. How these elements are connected. Let's say element number 1 is consisting of these nodes, 1, 2, 3. Element number 2 consists of 1, 3, 5. A list that says how the elements are connected to each other. These two define the mesh. In any complicated problem, it's the same. So these two parameters are important. And discretization is important depending on your problem. How much refinement you should have is an issue to decide on that. So you do a mesh convergence study. You refine your mesh, and you do it until you get to your converged solution. And this is called H refinement, and you can also refine the polynomials inside these elements. So the function, how it varies inside each element, you can refine it. Like I can use a linear element. This is a 1D bar element, let's say. It's linear functions. But I can add one more node. It can become quadratic. So it can interpolate quadratically, more accurately. Okay? So which one to use, it has to be decided by the designer. One thing that you should be very careful is also that when you're visualizing these softwares use some kind of nodal averaging. And so this kind of makes you lose some of your data, or some, like, if like this element has 1,200 megapascal, let's say this has 1,000, but on the average you see in the plot this, but actually maximum is higher. So you have to be careful with these discretizations. It's very important. So what this finite element consists of, it consists of a preprocessor where you define your geometry, mesh, boundary conditions. If you have a dynamic problem, you define an initial condition. We said mesh, you have to define a mesh. Pardon. Mesh consists of a node coordinates and element connectivity, and also you define the element type actually by defining this connectivity. You have boundary conditions, forces, displacements, and there's a solver which you define for linear elastic problems. It's not a big issue, but for nonlinear problems, you have to define certain parameters, convergence, tolerance, and steps, like steps of your load or some things like that. So we basically solve for internal external force balance, which is like given forces times, actually, this is the stiffness matrix. The inverse, you have to invert this stiffness matrix and multiply with your given forces. So this is actually, in the other form, is KU equals F kind of linear equation. And the post-processing consists of visualization of results. The procedure is the same for no matter what finite element code, or it's the logic is the same. So here as a 1D example, it's the bar example. Some people used to put it upside down. We have a bar. It has a fixed stand here. It has a load here. It has a length of L. It has a distributed load and the material properties, stiffness, EA. And the analytical solution says this. I put the derivation into the notes. Now, if I want to solve this problem by finite element, 1D finite element, what I do in the pre-processing stage, one is I have to define the material properties. Linear elastic is one-dimensional, so I have just defined a module. Geometric properties, E and A, L and A, and boundary conditions are given. Displacements, U is the displacement at x equals 0 is 0, and force is, this is strain. Strain times E is stress, times A is force, is given as this. So it's a function of the displacement, but its derivative is defined, okay? And what do? We have to assume an element type. Let's say let's use linear elements with two nodes where you see the element is defined by local length h. This is node A, and these are the interpolation functions or weight functions. So they have magnitude of unity at the corresponding node, but this has the magnitude of 0 in the other node. So this means when I'm interpolating displacements, a field variable, it could be displacement temperature, whatever you have always the exact nodal value at the node. I don't know if I can clarify it, but let's go on. So let's say if I have, like, this is the function, is it has a magnitude of 1 at x equals 0, right? And it has magnitude of 0 at x equals h, right? And this is the function of nb, right? It has magnitude of 0 here, and it has magnitude of 1. So we interpolate displacements inside this element using these weight functions. We can find anywhere at any position inside this element x, using these weight functions and using the nodal values, these are representing the node values, interpolated the displacements. So, okay, we can represent it in direct notation like this. It's just a multiplication, nothing about that. So displacements are in an element. In terms of the nodes, if you just rearrange the terms, they become, a function of x and the nodal values. Okay, I'll start a bit quicker. So we have to make a mesh. I used like 2 elements, okay? Let's say I have 2 elements. They have length of L over 2. So actually my local element size is L over 2. Keep a note of this. And we have the force FF, and we have obviously 3 nodes. And for first we have the procedure is as follows. We have to find local stiffness. So local stiffness says how you relate force to the displacements. Now, you see it is displacement gradient. This is strain. Remember the strain definition? It was a change of displacement. So it is a gradient. So what you do is you assume this function. We can take its derivative, right? You can take its derivative with respect to x. And it will become something like this. These are, the node values. So node values are multiplied by some number, and you get the forces. And on the next page, you'll see these are this is the multiplier of the displacement. So this is the stiffness, so-called. It's the stiffness of a bar element. And this is your one of the elements, okay? So it acts like a stiffness in one dimension only. It has one-dimensional displacement. Okay. And if you do it for the other forces, let me explain you this very simply. Like suppose you have this stiffness, you fix it here, you apply load here, okay, let's say, or you apply a displacement, let's say UB, okay? So UA is 0, UB is, let's say, some number. So the force in the other side has to have the opposite direction. That's where this negative sign comes from. Because of balance, right? It has to be on the opposite side. So indeed, you have this as positive sign, this with negative sign, which is actually a singular matrix and symmetric matrix. And this is a property of stiffness matrix. This is an elemental stiffness matrix. Now, we find the element stiffness. What do we have to do? We have the other element as well. We have to find it for it, and we have to assemble them, right? Okay, this is a little bit complicated. I don't want to complicate it too much, but you have to calculate the local forces. We can think of it this way, very simple way. Like suppose you have a distributed load here. A distributed load times the length of this is like F times L over 2, right? But I have to distribute this load to these nodes. I cannot put it somewhere inside here. I have only the nodes. So I have to weight them such a way that they're distributed to the nodes. They're equal anyway. So it's like a force comes here, FL over 4. Another force comes here, FL over 4. Like it's equal. In sum, they have the same effect. Okay? But you can take a look at this derivation, where this comes from. Anyway, what do? We said we're going to assemble it. We have, for the first element, it has an effect only to the nodes 1 and 2. it doesn't have any effect. This degree of freedom doesn't have any effect. So it's just on the forces, right? So it has just, these are 0, right? And also, it doesn't have any relevance for F3, so this rho is also 0. So this is like one of your elements' contribution to overall stiffness. You have the other one that acts only these 2 degrees of freedom, but in the overall, we want to get the global stiffness, where you sum these up. This is called the finite element assembly procedure. It's the same no matter what. It's the same procedure. Okay, so it's continuing. Now, we have the forces. We have to assemble the forces the same way. The first element has these forces acting only at these 2 nodes, and the second element has this other one. We have to sum these up. And in the end, we have this equilibrium equation. We have also reaction forces here. This is due to distributed load, this part, and there's also reaction forces. Anyway, then solution procedure. There are different ways of solving problems. One is to ignore the given degrees of freedom and reduce your matrix and solve just that part. This requires some treatment, so people do not prefer this because you need to bookkeep these numbers. It's not always very simple to find and eliminate the given degree of freedom, so it's not preferred anymore. There's direct modification. This is also, then what you do is, okay, you are given this delta, you put it to your force, and whatever you invert this becomes 1s again, so you get the same displacement as delta. That's very simple. So what other method is you multiply with a very large number of the diagonal elements that is specified, corresponding to the diagonal element that the degree of freedom, for the given degree of freedom. Okay. Then you solve the problem. Then you can find displacements. You can find stresses. You can plot them. So when we look at this is the analytical solution. This is the linear assumed solution. See the solution at the nodes, they are exactly the same as the analytical solution. Okay, so continuing on with the commercial application, the logic is the same. I used to show Abacus to show you this. There are different kinds of, first thing in the preprocessor is to decide on what kind of analysis are you going to do. Are you going to do a structural analysis, a modal dynamic analysis, a buckling analysis? Is it transient? Is it steady state problem? Things like that. And then you define your actual type of your problem. Is it a 3-dimensional, 2-dimensional problem? What kind of element type you should use? Then also your material type. Is it isotropic? Or is it composite? Now, for composite, we will look at this, but instead of just 2 parameters, we have here 4 different parameters or 4 different numbers to define. And also, if you have like Cengiz Hoca talked about a stacking sequence. You have different lamina layers, but they can have different orientations. So you need to say, okay, this is my lamina angle, or with respect to my sample reference coordinate. You have to say the angle of the lamina, so orientation of the lamina, and the stacking sequence. Stacking sequence also considers the thickness of this lamina. It's not just the angle, but also thickness can change. I will show you what it is. So, okay, you create nodes, you build elements, and you apply boundary conditions and solve it. For that, there's this application example in Abacus. I'll pass that. This is done for really training. I don't know if I should go through one by one, but you have it in the notes. This is pretty much the same for every software, but every software has different kind of intrinsic features. Okay, so there are so this is a preprocessor of how it looks the Abacus. So what you have to do is create parts, define material properties, create section. If you have a composite material, you have to say I have a composite layered material, and you have to assign this to the sections, create the assembly, load steps, and what output you would want. You want to see for Mises stress, total stress, or strains, displacements, whatever. And then boundary conditions and loads, and your mesh, and your analysis. Okay, there's this example, like we have a plate, very simple one. It is fixed at one end, and then it is forced at the other end. And you create the part, and you give the material properties here. Like for isotropic material, elastic material, you only give two properties. That's elastic modulus and Poisson ratio. Okay. And you define this section. It's special to Abacus. Some software doesn't have this section option. You have to tell, if it's a 2D problem, the thickness of this plate, and so assign this section properties and some other things like the solution, load steps. Is this a linear problem, a nonlinear problem, a large deformation problem, or so, and things like that. There are some specs. I'm just passing them quickly. And the field outputs, what kind of outputs you want to see, you select them in a tab. When you click on this, this appears, and then you select some of these options. And then you analyze it. These are for boundary conditions. And in the end, you enter, this displacement as 0, and these are, you apply force here to this end, and then and you create your mesh. This shows how to do it. Then you create your model, and then you analyze it, you get your results. Okay, strains or stresses that you want to have. This is a very simple case. Okay, so what's special do you have any questions with this part? I'm just sorry if it's too intense or too much or too boring. Sorry to, I hope I won't get you bored in this. Sorry. Okay. For the composite mechanics, I divided into, first I will mention the motivation. Again, I have some definitions. First, I will talk about lamina mechanics. It's also called micromechanics, the lamina they refer to. In some books, it's called micro. And also, then I will talk about how to calculate the stiffness transformations, how to transform the lamina stiffness to your XY sample coordinates. And laminate mechanics. Laminate mechanics, also called macro mechanics. It's more macro scale. Okay. And then I will again show how it applies to commercial FEM application. There's an interesting problem that my student worked on. So I think Cengiz Hoca quite much mentioned about the motivation about using composite materials. Mostly they are used in aerospace industry. We have seen interesting applications to Composite Center. A guy came with this, they create these masks or something that out of composite materials that they can easily carry out and easy to open these telescopic parts. So there are different military applications, railway applications. Also, I used like this, my old BlackBerry phone. It was very good, I think. And also automotive applications are proliferating. So let me go through what Cengiz Hoca defined. We have unidirectional composites where you have fibers along one direction and you have bidirectional ones, okay? And there could be also chopped fiber case or discontinuous fiber, or these fibers could be woven. So composite material, first of all, it's actually by definition two materials coming together to perform better. Okay, so better than its constituents. Overall, what do we mean? Fibers, okay, fibers are strong, but you need to hold them together, and they don't have shear strength. So matrix provides the shear strength to them. And like matrix is weak, but fiber increases its strength. Okay, so it's some kind of like that. It's a compromise. And yeah, like I said. There are different kinds of laminates commonly used in the industry. One is symmetric laminate, which says laminate angles are symmetric with respect to the center of the laminate or neutral axis of the laminate. You can also show, it's also shown with these angles. Let's say these start from the bottommost layer. It's like 30, 10, 30, 10, 10, and 30. And it's just shown with an S sign for the symmetric laminates. Regular refers to the thickness. Balance means it's a slightly different one. If you have a theta, you have always another minus theta. Or if you have 0, you have a 90 degree. So I'll pass this quickly because I cannot make it, I think. And you have different kinds of other definitions. Cross-ply has only 0 and 90. Angle ply has plus minus thetas. Okay? So like I said, this is kind of a description that you can find in the book. So you have these angles. It starts from the bottommost layer. It goes toward the top. There are different representations. It's symmetric for other cases. So this also Cengiz Hoca passed, but I will just slightly mention. So how to find the longitudinal modulus out of fiber and matrix moduli. So when you think of this, it's called also Taylor or isostrain assumption. These two materials, let's say matrix and fiber, they co-deform. They have to deform compatibly. They have to deform, they are exposed to the same strain. They must carry the same strain. So it's called isostrain assumption for that reason. So it's called, so different homogenization is used for that reason. For the lateral modulus, it's more like force equilibrium has to be satisfied instead of compatibility. So it's called isostress homogenization. So I use a different homogenization to find the moduli. Okay, but on the other hand, actually, there are good approximations theoretically, but in the experimental behavior, material behaves different than theory. It's never like also Cengiz Hoca mentioned, there are defects in the material, there are other things. So you can directly measure this. Instead of doing this, we usually go to lab and measure those terms. Like we do tests along, let's say I want to measure E11, I do tension tests along the axis of the fiber of the laminate. I put several lamina together, make one lamina in one direction, and then just do test. Get this experimentally. It's more accurate because it's different. Okay, and so like we said, slightly different from the 3D material, we have a smaller compliance here. It is called reduced compliance for that reason. It's two-dimensional. And like we said, but you have different longitudinal modulus. So stiffness or compliance, doesn't matter. They are different for both directions. It's stronger in fiber direction, weaker in the lateral direction. So these are two different numbers, okay? This has to be symmetric. So you have only Poisson ratio different, and the shear modulus also is different. So you have 4 independent parameters to define the stiffness of a lamina. It's different from the isotropic material. For isotropic material, we have 2. For composite material, composite lamina, we have 4. Okay. So you can invert this to find the stiffness Q. I just didn't directly start from this, so you don't want to see where it is coming from. It's more complicated. So we have these Q terms. Usually Q is used for stiffness. It's called reduced stiffness. Matrix, it's called reduced because it's two-dimensional, right? So it has these components. I will go from here. There's an example. You can check this out, how to calculate the stiffness. I put it there. Maybe you would use it, I don't know, for some reason. And then, okay, what do we do? Let's say I have this lamina oriented with a theta degree from my sample coordinate. I need to transform that stiffness, right? How do I do it? With a transformation. I'm not going to go through this in detail. This is called a passive transformation. It's not, you don't say this is my lamina. Actually, I'm not rotating this actively. I am just changing the frame. I'm looking the same thing in a different reference frame. That is called a passive transformation. The other is called an active transformation. So this is, there's a negative sign here. for that reason, but these are some detailed information, but I just want to say the difference because it's different. Okay, and so what we do is we transform, it's actually here. If you transform stress components, you end up with this expression. You may check out this derivation. I have to speed up here. So what do we do is first, let's say I have a strain in XYZ. I have always my displacements defined in XY frame, my sample frame. So from that displacements, I can calculate strains. So I have always these strains at XY reference frame given. Now, I want to have the strains in this reference. First, I transform them, right? But this will give me the engineering strain. So that was the point I showed you at the beginning of the slide, why it's different. This is different. It is simple shear. So it was double of this. So you need to have some scaling there, which actually, if you don't put this, your whole calculations will be different. Anyway, that's some detail. And then what do we do? You apply stiffness. You can find the stresses in the lamina coordinates. Then you need to also transform it back to your sample reference frame. So there are two transformations which transforms your lamina stiffness to the XY or coordinates, or your sample coordinates. So I'll just skip. These are the equations that come up with that. So this is the fourth order terms here. It's an example. There's an example. I put it there so to illustrate it. Now, now, how do we deal with this laminate? There's a Kirchhoff theory. I'm not going to go through it. Please refer to any books because it's too detailed and we don't have time to cover that. But I try to explain it here. Take a look at these displacement expressions. Basically, we have, I'm not going to go through it. In the end, you have some forces, and you can relate them to some in-plane strains and curvature. Because plates, they bend, right? They can bend in one direction. They can also bend in the other direction. And they can also twist, right? So these are these curvatures. And you have also the strains, in-plane strains, like in-plane strain. Like I'm tensioning it at one direction, and I can also tension here, and I can also have some shear, right? So all these deformation modes for that plane are here. And you have some stiffness terms, and that relate to find the forces and moments. Okay, so these are called the stiffness matrices for this laminate, sorry. So what it consists of, let's say this is in-plane stiffness term. That relates the in-plane strains to forces. It consists of some transformed stiffness terms, okay? And their sum is, this comes from the sum, it's actually the thickness of these laminae. So it's the sum over the laminate, okay? And we have force curvature coupling. I will come to that. And we have the bending stiffness, this D. It's proportional to thickness cube. Okay, this is an example again here. You can check out how to calculate those. Then, okay, before moving on, okay, let's move on. Let's not stop here. So I put these examples. Also, you can check these out for the plate case. Now, actually, this was an interesting example to show the potential of composite materials. We applied to a cylindrical tank. We used first the steel. Actually, my student did that. So he modeled with an isotropic material, that part with the pressure loads and everything, and he finds this mass for these maximum stresses. And then he used also composite material. He defined these numbers. Then he defined this layup, like the angles of these laminates. And then he found out that this, this is a better stress. It has the same scale, I guess, and but with a much lower mass. And he did some more optimization, like he tried to reduce the thicknesses because the pressure is higher here, not much higher here. So he did some more ply drop-off studies, and he looked at different cases, and he did some further optimization. Okay, so this is actually what I want to talk about in the last 10 minutes. So how do we use this information for the design of variable stiffness composite, and why do we need it? Why do we have to do this? Because software already does that. Why do I need to learn finite elements technically? First of all, I need to describe what variable stiffness is. This is a tank manufactured in NASA. It's a cryogenic tank. This is done by some robotic manipulator. It has like prepregs, toes. They are compact, like say there's a mold, and it goes to a mold, applies some force, and applies also heats up the prepreg so that they can easily lay it up, or it can make it stick to the mold, and manufacture these parts. This way, it's possible to manufacture parts with complicated geometry. You can get weight reduction. You can get structural stiffness. You can tailor the fibers. You can lay them in the directions you would like. And there's manufacturing automation also, which means product quality instead of hand layup, and repeatability and reliability, basically. Okay? So, and decreased labor costs. And you can manufacture complex geometries. Yeah. So what do we mean by what's different from the constant stiffness? Constant stiffness, you have these laminar layers in all one direction. Now, for variable stiffness, you can have it differently in the laminar layer. You can lay it in the directions you would like to have. Of course, there are limitations for it. Also, constant stiffness refers to you can have a constant thickness. Also, you can have thickness variation. Always, you should keep in mind that you can also change the thickness. That also refers to variable stiffness structure. So think about a simple problem. Let's say I have a mesh 10 by 10 with 100 number of elements, and I have 10 alternative angles, okay, for each element. This is a very coarse mesh I'm talking about, and I just put this example to show that it's not possible. So you have 10 angles for 100 elements. You have 100 times possibilities, right? 10 to the power 100. If you were searching among these possibilities, let's say I have 1 millisecond of calculation time, and that makes that much of seconds, that much of hours, that much of years. It's not possible to do this calculation, to decide on this. So you need an optimization procedure. Another challenge is once you start laying up these fibers, it's possible to have fiber buckling, or some other defects can show up. So there is also always a manufacturing limitation for this method. So what did we do for this research is we developed a method, an optimization method in finite elements, and we find the lamination configurations considering the manufacturing constraints. So the optimization runs the finite element analysis several times. This requires the calculation to be done in the same environment because it has to be efficient. You know, we use MATLAB, so MATLAB has optimization tools, everything, so that we can have access to. So that's why we need to do all this implementation. Now, there's one definition that is very often used in composite materials design. It's called lamination parameters. I will skip the definitions, but they are higher order sine terms, sines and cosines basically, trigonometric functions. Actually, they have one use. I'll just come to the result. Our stiffness matrix for the plate it becomes a linear function of this stiffness, this lamination parameters. It's not a function of cosines and sines anymore. It's just a linear function of this parameter. This is a material invariant, meaning it's invariant of the lamina orientation. They're just constants for a lamina. And this is the thickness of it. So U is just material constants, like Q's and other, or they are made by modules. You can calculate them from the modules. Okay, and so I will skip the finite element method we used for the plates. It's a plate deformation theory, so it's a little bit boring. I'll come to the fun part real quick. We did some patch tests. We developed these elements. We did some tests on different boundary conditions to make sure that it's working. Then we optimize. For the optimization, we minimize the compliance. Actually, we maximize the structural stiffness. And compliance is defined, or compliance or strain energy is defined like this. Compliance is actually twice of the strain energy. And you need the function. Your objective function is this for the optimizer. And the function's derivative for your parameter. Our parameter is lamination parameter in this case. And we have some constraints due to trigonometry. I'm not going into details of this. So in the end, we have a finite element mesh. We have different boundary conditions. And we want to find the optimum fiber angles given for this mesh. Okay? That's the idea. So that is the thing. I'm not going to go through this. Let's say for a simply supported plate, I have this. I have a plate, and I have a pressure load on this plate. There's a uniform pressure on this plate. Now, this is the optimization result. That is the lamination parameters. We did check the optimization method by this way. We assigned each element a random initial guess, and we converged to the same result. That's very important. Check. That shows that your problem is convex, and you can get to the local minimum. This is when we convert these lamination parameters to the angles. This is the optimization result for, let's say, a single layer. So when I have a simply supported case, if I can put these fibers in this form, I would have the optimum response. Okay? It's like 20% improved with respect to the constant stiffness, best constant stiffness solution. But see, if I'm a machine, I cannot manufacture this, right? Or I don't know what to do here. I cannot. There are gaps here. So we used another method to connect these points. It's called a different method, but to connect these points and make them connected. Okay. For the fixed plate, again, pressure load, but fixed case, we have this. So the optimum solution gives us this, and we can convert them to manufacturing paths using the limit, using a curvature limit. And for like cantilever plate, it's not very common to load plates here. Let's say I fix this plate. Actually, this was, sorry. It's fixed here and load is applied on top of it. So it becomes like this, the optimum solution. And when we apply our method, it becomes like that. So, and another thing that we recently applied to a open hole case where you need some holes in composite materials. So this is a biaxial load case. This is the optimum angle distribution we have. And this is when we apply our method here. See, these are the stress results. You can think of this as stress concentration factor. For the constant stiffness case, it's 6 or 6 point something. But for the optimum one, it reduces 1/3 of it. So it's very significantly improved. If you have an open hole tension case where I pull this part along just here, see, it doesn't, the stress, it arranged the fibers such that stress flows see through like sideways of the circle, not through the circle, okay? So it does work in such ways. Okay, we published this in a recent paper, whole thing, and I suggest if you're interested, this is a very good reference. You can find this book online. So I think many of the things you can find this in this presentation, you can find it online. So, or if you're interested, you can also ask me. So I think that's all. I owe this research to my research group. It has been 2 years I've been working, but we started growing. And thank you. If you have any questions, I'll be happy to answer it. I hope it was like too fast.
Well, I would be interested in thinking some simulations like I have a material, a mold, injection molding machine mold, special shape. My material is polyamide, but I want to make some cost efficiency using polypropylene with glass fiber reinforcements. Which materials should how will I configure the, by the way, we use SolidWorks for simulation, and some of our joint research bodies uses ANSYS. How will we enter the elastic models and Poisson values or material properties of glass fiber, chopped glass fiber with polypropylene?
If it is chopped, I think it's easier. It's called transverse isotropic material. Transverse means in transverse direction, material properties are the same. So for that, there is little that you can do for the optimization because you don't have to decide on the angle orientation. So it's pretty much.
How will I define the material? Because the designer or the user,
I
call them the operator.
Okay.
The operator of this program, and he asks me the material. What is the material? What is the elastic modulus of the material? And okay, there is glass fiber in it, and there is polypropylene with a certain MFI and viscosity. Maybe I can tell.
If I were the designer, I would look at the fractions of each constituent and make an like a average homogenization, like volume based on volume fraction of like polypropylene or the other material, and then based on that, I would try to analyze for the application. You know what?
I have no idea about the distribution or dispersion of chopped glass fibers.
It's okay because it's. If you are not interested in the local variations, I mean, if you're interested in the major.
You are familiar with the ISO 527, the tensile test methods?
Yeah, we do it a lot of testing in our institute, but I'm not the testing guy to ask. He's the testing person, actually. First of all, if it's material design, what we do is, okay, you put different constituents on materials, and you do tension tests, and you characterize them. You know, you get the like how much, 10% polypropylene, I'm just random, and remaining 90% the other material, and mix them up, do the tension tests, and this is my, result.
So
characterization. And then use that.
That's why I said ISO 527.
And use that characterized information in the model, like the properties. Like modulus values, everything from that tests. It's better always. Testing is always better.
Okay, this answers my second question also.
Okay.
I had one.
In theory, homogenization is, materials do not behave ideally. There are always voids or different things happen due to processing. So it's always to do tests and characterization and use that response in the model. Exact response of the material for the design. Okay. Any other questions?
I couldn't find your presentation in these copies.
Yeah, actually they're gonna.
Load or not allowed?
Pardon, bastıracaklardı ama herhalde var mı? Tamam, çıkışta vereceklermiş. Tamam. Dışarıdan alabilir misiniz? Yok, gizli hiçbir şey yok. Yani biz publish ettik zaten. Yani public oldu demek anlamına geliyor bu zaten.
Yani internetten dolaşabiliyorsak o da problem değil.
Sonuna kadar dinlemeyenlere vermiyoruz diyorsun.
O yüzden çıkışta masalarda çıkışta
Kahve makinesinin yanında.
Kusura bakmayın eğer biraz tam böyle bir yaza yakın bir gün, güzel hava, biraz sıkılsak.
Hocama teşekkür etmek
Ben
istiyoruz.
teşekkür ederim.
Şöyle alalım hocam sizi.
Teşekkür ederim.
Ben tamamını dinleyemedim ama çok teşekkür ederiz.
Ben teşekkür ederim. Çok sağ olun.
Katkılarınız için.
Çok sağ olun.
Bugünün anısına
teşekkür ederim. Onur duydum. Çok
plaket
sağ olun.
vermek istiyoruz.
Çok sağ olun.
Evet, tamam mıyız
Tamam.
arkadaşlar? Ha, pardon. Fotoğraf mı alacaksınız? Peki.
Şunu da bir arkamıza bakıyoruz.
Peki.
Kusura bakmayın, yorduk sizi.
Bir tarafa taşıyoruz. Peki, tamam.
Orada biraz köşede kalın.
Tamam, peki.
Bir daha alacağım. Taştan gidiyorsun.
Çok teşekkürler.
teşekkürler.
Çok sağ olun.
Çok sağ
Çok
olun.
sağ olun. Teşekkürler.